I think it's another day. I had a 2-week regimen of hydroxychloroquine, and I've taken it, I think, just about 2 weeks. I think it's another day. So, and I'm still here. I'm still here. And I tested very positively in another sense. So this morning, yeah, I tested positively toward negative, right? So no, I tested perfectly this morning.
You know, there's been a lot of talk lately about test results, and getting test results clear for people is not always straightforward. So I thought it might be worth 5 or 10 minutes to sort that out. So we want to talk about the prevalence of a disease and whether a disease is actually present in your population. And so here you get a concept. Maybe this is all of the people that get tested. And what we will know is that some of those people who get tested actually have the disease. And just to get our terms right, we refer to the people who have the disease as positive. And they are positive for the disease. And those who actually don't have the disease, we refer to them as negative. And this is not always intuitive to everyone, but it's important to understand that having the disease is positive and not having the disease, at least in the terminology of the statistics, is as we show it on this chart here. Now, what's kind of interesting is that in an ideal world, we might have a situation that looks like this, where this is the population of people that have the disease, and we're not going to have a test, and we're going to do a medical test. And what would be great would be if that medical test performed exactly as you might expect the reality of the disease is. But in fact, we know that doesn't really happen in medical testing, and we're going to give you a couple of examples of that. But now let's say, for instance, we actually have the same situation with the same prevalence of the disease. Those folks actually have it. And what we're going to do is we're going to run a test, and here's a test that overlaps the population that actually has the disease. And we would say, hey, if the disease is present in the patient, remember these Venn diagrams from when you were in elementary school? If they actually have the disease and the test said they had the disease, we're going to call these true positives. The test was positive and it was true. Now we'll have all of these folks over here who really did have the disease, but the test said they did not. The test is essentially a false negative. The test called it, you're safe, you're negative, but in fact, you had the disease. Now over here, these are people, by the way, where the test said you had the disease, but you didn't actually have the disease, and we call these people false positives. And of course, those people who don't have the disease, and the test said you don't have the disease, these guys are true negative. So now you can understand there's this concept that you're going to see over and over called a confusion matrix, in which the false negatives, the true negatives, the false positives, and the true positives show up on a chart. Now, let's do some thought experiments to see how this works. So let's say for the moment that we have a situation. Here is all of our people. These are the people who actually have the disease. And let's say for a moment that we have a test that performs like this. So let's just kind of look through it and say, hey, what could be going on here? These, of course, are true positives. They have the disease, and the test said they had the disease. Now, all of these people in here are people who the test said had a disease, but they didn't really, right? So these guys are false positives. And of course, out here we have true negatives. And what's interesting here is there's no false negatives in this particular case, right? So let's think about what might this be. And let's say, by the way, that we know that most people who have a fever have an increased temperature. That's actually almost the definition of a fever, not exactly, but pretty close. But we know that those are related concepts. So let's say we had a test that looked at temperature, and we said if your temperature is greater than 98.6 degrees Fahrenheit, then you have a fever. What's interesting about this is if you actually have a fever, your temperature will be over 98.6. But what if you've been exercising and you've been exercising out on a summer day, and now you set your temperature is 100.0 degrees Fahrenheit. Now, in this particular case, your temperature is over our threshold, so now you are positive by the test, but you don't have a fever. Here's an example of people that are false positives for a test that only looks at temperature. So these are the people who have been exercising, and these are the people who have a fever. Now, of course, it's not always that simple, but let's explore the opposite situation. Now, let's say we have a test. Here we go, all the people who have been tested. Here's that same group of people who have actually have the disease, and let's say our test does this. So now our test only captures a portion of the people that have the disease. Say, that's an interesting situation. Let's say, for instance, that we noticed that most people who actually are pregnant are women. I actually don't know of anybody without a uterus that can be pregnant, but that I suppose could change. So now what we could do is we could have a test that actually looks at pregnancy and decides whether or not that person, based on their pregnancy status, is female. And we would say all of these people right here were positive for pregnancy, but there's a whole bunch of women out here who are female but not pregnant. And there's a test that just isn't helpful either for us. It's got its own set of problems. And so we have to be really careful about our test design, because you could end up with very bizarre results, right? Let's look at a much more common way in which the tests are set up. And here's an example where we have all the people who have been tested, and we have this group of people here that are positive, and then we have a test that overlaps it like this. And we talked a moment before that these are true positives. These guys over here are false negatives. These guys are false positives. And then these guys are true negatives. And you may recall that from before. We want to define something we call the sensitivity of the test. And so the sensitivity, actually, what we're going to look at is how well does the test capture all the people who actually have the disease or the condition we're talking about. So what we might say is that the sensitivity of a test is equal to the true positives divided by all of the positives. And in this particular case, what it would be equivalent to is it's the true positives divided by the true positives plus the false negatives. And in this particular case, you can see what the situation might look like, and you can actually calculate a sensitivity. Let's say for fun that there are 10 people in here, and there are 2 people in here. Our sensitivity would be 10 divided by 10 plus 2. I'll let you do the math. It's going to be a number that's in the pretty high percentage range. You can say that's a pretty good test. Now, you could imagine, by the way, we'll just do a slightly different test, and it's going to be a smaller version of this just to save a little bit of room. Here's the true positives, and now let's say we have the group of patients. Now, let's say in this particular test, there's a lot less overlap. And we might actually say that in this particular case, you've got 2 patients in there, right? And you have then 10 patients in here, right? And so now your sensitivity is 2 divided by 10 plus 2, and you're going to have a relatively low sensitive test. And that's because your test doesn't overlap reality very, very well. Now, what I want to do is to look actually at the same scenario that we have over here, and we're going to define something called specificity. In the case of specificity, we're going to say that this is the true negatives divided by all of the negatives. Let's get our head wrapped around that. The true negatives is everything out here, all of this, right? divided by the other negatives. What are the other negatives? Well, that's the true negatives is the true negatives divided by the true negatives plus the false positives. So in this particular case, we're going to add in the false positives, all of these guys in here, right? Now, if you have a test that looks a lot like the ones we've been looking at, we would essentially say, hey, in this particular case, you could do the math and assign it. And you can imagine a test that has very good sensitivity with very poor specificity, right? Or, by the way, the example of that we had from before, where if you have very, very good sensitivity without good specificity, you get a test that looks like this, and you end up essentially saying everybody who has a high temperature has a fever. And you can end up with exactly the opposite, where you essentially have a test that looks like this, where you essentially say everybody who is pregnant is everybody who is a woman is pregnant, and of course that's not helpful. And so we're on the way to starting to figure out what is the impact of sensitivity and specificity as we think about test results. Now, there's one other factor that really matters and is pretty important to understand. So here's everybody that's been tested, and let's actually think about the high prevalence versus low prevalence. So here's a disease that's high prevalence. So a lot of people in the population have this particular disease. And if we were to compare that with low prevalence, we would end up with something maybe that looks like this. This is relatively low prevalence of the disease. So this interaction between sensitivity and specificity and the prevalence of the disease is pretty important. And to understand that, what I thought we'd do is we would actually look at a little simulation that I built in Excel to help us to understand how these relationships work. So here's how the simulation works. We have a population of 1,000 patients. Here you can make it 1,000,000, or whatever number you want it to be. And in this particular case, we're going to talk about the prevalence of the disease. This is the ground truth about what fraction of the population actually has the disease. And in this particular case, I've set it to 50-50. That's almost never reality, but it really is helpful for understanding the way in which these tests interact. So here's the situation here. We have the confusion matrix. Remember that from a few minutes ago? Confusion matrix says, hey, of the 500 patients who actually have the disease, 475 of them actually will test positively. That's because that sensitivity is set to 95%. And then we'll have, of those 500 people who are truly healthy, 475 of them will actually show up to be healthy. And that you'll see that as we look at the specificity number in this. Now, what's happening here is that under these test conditions, we still have 25 people in each of these two categories that are getting bad test results, or to put it another way, their test results are misleading. So we have 25 people out there that got a false negative test. So they're wandering around out there saying, I'm healthy, when in fact they are unhealthy. And we've got 25 people out there that are worried, but for no particular reason, because we told them they had a positive test result, even though they are perfectly healthy. And that is related, again, to the sensitivity and specificity of this test. So let's take a look and see what happens. If I drop the specificity, watch what happens. As I start to drop the specificity here, the number of people who are perfectly healthy but end up with a positive test starts to increase. So if your specificity is low for the same given sensitivity, you're actually going to get an increase of positive tests without any real increase in disease. And what you're going to do is increase the number of people that are worrying about their health status, even though there's nothing for them to worry about. Now, I'm going to, let me set the prevalence back to 50 here. Now, let's take the specificity, I'll put it back at 95%, and let's start to drop the sensitivity. Now, as we drop the sensitivity of the test here, what you start to see is that there are a number of people here who have the disease. That hasn't changed. That's still 500 people out of that 1,000, 50%. But now only 325 of those actually know they have the disease, and 175 of them, that's these guys right here, are wandering around with a negative test result, thinking that they're perfectly healthy, but in fact, they actually do have the disease. So let's set this back now and let's watch to see how it interacts between sensitivity, specificity, and prevalence. And I'm going to start to move the prevalence down, and I'm going to move it to about 10% because that's the current testing rate for COVID in a lot of places around the country. And in this case, I've got very high sensitivity, I've got very high specificity, and actually now I have a prevalence rate that is pretty low, a few percent. Now, under this particular circumstance, you can see that out of the 900 people who have a perfectly healthy situation, 45 of them now are going to be the worried well. These are the people who got a positive test result but are perfectly healthy. And that would be, here's the well and they know it. Here are the people who are well and they're just worried because they got a positive test. You can see those connected right here. Now, at the same time under this circumstance, we have 5 people who think they're perfectly healthy, but they're not, and 95 people who are sick and they know it. And you can see that that prevalence now has actually changed the relationship between those who should worry and those who don't. And one of the things to look at is the false positive rate compared with the false negative rate. What we've chosen when we've built a test that looks like this is to say we would rather have 45 people wander around unhealthy, or we're going to have 45 people wander around worried about whether they're healthy, and 5 people who are out there saying, hey, I'm perfectly good, but I've had a negative test. Now, reality here is that you almost never have a test that's 95% sensitive and 95% specific. And so I'm going to knock this down to something that's a little more reasonable, perhaps 95% sensitive and 75% specific. And let's see what happens here. Under this condition, and this is not unusual, you will have, in fact, still 900 people out of the 1,000. Nothing changed here with the population size and nothing changed with the prevalence. You still have 100 unhealthy people and 900 healthy people. But now you only have 5 people wandering around thinking that they are healthy when they in fact have the disease. And you have 225 people wandering around worried. And this is the situation that you run into because you actually, in this case, you know a lot when you say you have a negative result, because that means you're very, very unlikely to be in this red box and you're very, very unlikely to be in the pink box. You're probably in the green space. Whereas if you have a positive result, you could be in this particular green box and you could be in that red box, and the positive result doesn't necessarily in this case mean you have the disease. But a negative result is very, very strong evidence that you don't have the disease. So as you talk with your friends and others who may have had tests, it's helpful not only to know whether they had a positive test or a negative test, but to know what the prevalence is in your population, and then to know what the sensitivity and specificity of the tests are that you're actually using to measure this. So that's why it's important for you to know more than just, is it positive, is it negative, and was the positive actually good for me, or was the positive negative bad for me? And you can see I'm even confused in the end of this. But the truth of this in the end is that sensitivity and specificity of tests are important, and the prevalence of the test will affect the way that sensitivity and specificity have meaning for us as we try to interpret our test results.